true. You're the one that I want. Ooh, 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 honey, the one that I want. Ooh, 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 honey, the one that I want. Ooh, 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 can't you see? Oh yes, indeed. Oh yes, indeed. If you're filled with affection, you're too shy to convey. Meditate my direction. Feel your way. You better shape up, 'cause I need a man who can keep me satisfied. You better shape up. You better prove that my faith is justified. But I'm sure down deep inside, you're the one that I want. Ooh, 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 honey, the one that I want. Ooh, 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 honey, the one that I want. Ooh, 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 can't you see? Oh yes, indeed. Oh yes, indeed.
I met you at your cornerstone. Now I'm betting I could beat you home and delete the pictures from my phone and drown myself on court to Rome. I believe in love, but I'm bleeding out. I can feel the fire because I'm feeling low. You can call my mom, tell her I'm the one. You can call my mom, tell her I'm the one. I'm a saint till I ain't, till I ain't, till I ain't. When you figure it out, then you know. Pain in the chest, it's a shape, it's a shame. The promises made years ago. Now I need a pacemaker, I'm old. Should've never brought you along. I'm a saint, I'm a saint, I'm a saint. I'd rather be a plagiary. Unique among the friends I keep. I believe in love, you gotta feel it out. If you're losing fire, gotta stomp it out. Just don't call my mom, tell her I'm the one. Please don't call my mom, tell her I'm the one. I'm a saint till I ain't, till I ain't, till I ain't. When you figure it out, then you know. Pain in the chest is the shape, is the shape. The promises made years ago. Now I need a pacemaker, I'm old. Should've never brought you along. I'm a saint, I'm a saint, I'm a saint. I'm a saint. I'm bleeding out. Bleeding out. Bleeding out. I'm bleeding out. I'm bleeding out. Please don't call my mom, tell her I'm the one. Please don't call my mom, tell her I'm the one. I'm a saint till I aim. When you figure it out, then you'll know. Pain in the chest is the shape, it's the shape. The promises made years ago. Now I need a pacemaker, I'm old. Should've never brought you along.
This is a fill-in talk. There was a cancellation. You know, people get sick and things, so I've done this one before, but not here. My name's Richard Campbell. I make a lot of podcasts. Any podcast listeners? A couple? Yeah. So this is from the Geek Out series. So .NET Rocks we've been doing since 2002. We're in the 1940s now, so I always do a little history lesson at the top of each show. It's like, what happened in 1947? Run As is my IT show, which I've been doing since 2007. And for a brief interval, we made the tablet show when we didn't know where tablet stuff should go. And recently I joined Windows Weekly because doing 2 podcasts a week didn't seem to be enough, so why not 3? And this is from the Geek Out series. So starting back in 2011, we started doing 1 show a month on .NET Rocks that was whatever geeky subject the audience wanted. And eventually that spun into a set of talks. I did one on building bases on the moon, and then NASA called, which is weird. I didn't believe it at first, but no, it was really them, and they're like, we really like your talk on moon bases. I'm like, oh, it's nice, thanks very much. They're like, would you ever consider doing it as a presentation? And I'm like, yeah, I guess. They only know me as a podcaster, right? And so, do you know PowerPoint? We like PowerPoint at NASA. I'm like, yeah, Chuck, I know PowerPoint. It's like, okay, well, like, can we figure this out? I'd love to have you do a presentation. I'm like, okay, well, to who? Well, to us. It's your stuff. Yeah. So you want me to present your stuff to you? Yeah. All right. So I got to go to the Ames Research Center, which is outside of San Francisco, and that was on the entry board going in about building bases on the moon. And then the word got out that I'd done this talk for NASA, and the conferences said, well, can you do that talk for us? And I'm like, okay. And so now I do Geek Out talks every so often. And I'm going to do 2, one today and one tomorrow. So tomorrow's one is on the future of energy, but I tailor those ones specifically to the local market. So I have spent the past couple of weeks reading about power generation in the state of Victoria. It's, we'll go there if you want. We debated whether to do a whole hour on nuclear just because I know how a hot topic it is here, but we'll just do a little bit tomorrow on it. So why be a spacefaring civilization? This talk that I did for them was much more about it was really about building a research base. So we've gotten to a point now technologically where a bunch of scientists are fairly confident that they could start staffing a facility on the moon at regular intervals, sort of like Antarctica. Their plan would be like 42 days at a go. So there's a day-night cycle of about 14 Earth days on the moon. So you sort of 14 days of sunlight, 14 days of darkness, 14 days of sunlight, come home. That would be the model that they were proposing back then. And that's evolved a bit. It turned out there's some more military applications that are interesting. The Chinese are an active part of the equation. But those are all, nationalistic experiments. If we're really talking about us from a society perspective, why bother? Well, one of the arguments would be the dinosaurs died out because they didn't have a space program. So one of the upsides to having a space program is that we do have an opportunity to deal with potential extinction level events. In fact, NASA has an whole organization around planetary defense. Most of the time we think about that in the context of asteroid defense, but it's actually a bunch of things. One of the geek outs I've done, if you go back and listen, is the one on supervolcanoes, and that comes from a NASA paper that talked about the risk of the Yellowstone supervolcano erupting again. It has now erupted every 600,000 years for 1.8 million years, and the last time it erupted was about 600,000 years ago. Not that these things really follow patterns, and what NASA's proposal was, is in order to avoid another eruption, that we build a series of geothermal power plants around it and pump the heat out and make it into electricity to keep the caldera cap in place so they don't have an eruption. It's an interesting idea. It would not make the Yellowstone Park look very nice when they were done, but it's possible. The last supervolcano to erupt is not far from here. It's Lake Taupo in New Zealand. erupted about 30,000 years ago. And you're talking about a worldwide cooling event if another supervolcano goes off again. Kind of a big deal. So planetary defense covers a lot of different things. We have made progress on the asteroid defense side. There was a mission a few years ago called DART, where they deliberately impacted an asteroid to alter its trajectory. It was an experiment. Is this even possible? The asteroid they picked was actually a binary asteroid set. So there was the larger asteroid called Dimorphos, and the smaller asteroid they ended up calling Didymos. And that's not its actual name. And the smaller one is orbiting the larger one. And so the idea is let's hit the smaller one and see if we can change its orbit around the larger asteroid. Like, is the kinetics even made sense? And they did it. It actually worked. In fact, this is a video sequence, actually a series of photographs taken from the DART impactor as it's approaching the asteroid. So these are shots about every 5 minutes. It's really moving fast at this particular moment. It's like it's 7 kilometers a second as it comes whizzing in towards the asteroid. The asteroid itself is 160 meters across, and this impactor is moving. It weighs about 500 kilos, and it's sending back photos and sending back photos. And here we're slowing down frame by frame, and you'll notice one of the frames doesn't quite finish because. And then a kinetic event happened. Now, cleverly, they had also launched a pair of small nanosats off of the primary impactor about a week before. So they were now some distance behind and were able to actually get footage of the impact. Turns out that the asteroid's actually a rubble pile. It's just a bunch of rocks conglomerated together. And so the impact substantially changed the orbit, more than they expected. They were hoping to change it by a minute or so. The current orbit is like a day, and they changed it by over half an hour. And so there's this whole weird set of kinetics when the impactor hits and shuffles through all this rock. It's created this massive ejecta tail that's trailing behind the asteroid assembly now. And there's another mission on its way to go and evaluate what they've done now a few years later. So we're actually working towards real asteroid defense. Like, this is a thing. We can do this. We can map the behavior of asteroids well enough. We're getting better at spotting them. You may remember Oumuamua, which is this asteroid that actually came from outside of the solar system with enough momentum that it did a pass by the sun and then now is headed out of the solar system. It's going too quickly to stay. And it's not that we've never seen one of those before, and that's not because they haven't happened before, but because we now have better instruments able to detect these asteroids coming from various odd aspects. And so bit by bit, we're getting a better map of the asteroids that are relevant to us and can actually provide defense to them. And possibly, manage to not extinct ourselves, at least not that way. Obviously, one of the opportunities here would be to do resource extraction from asteroids at some point, not just to knock them around, but to keep ourselves from getting hurt. So, and the argument for getting into space is that we take advantages of the resources that are in the solar system, not just on our planet. There's an argument, I read a great paper on this from NASA, that said that we are in a narrow window of time where many of the key minerals necessary for spaceflight are relatively inexpensive and easy to acquire, but that we will use them up in about the next 50 years. And if we haven't established the ability to extract those resources from other parts of the solar system, we probably never will. And so there may actually be a deadline to our civilization's ability to become routinely traveling in space and to use the resources that are available out there. The Americans, of course, have been pushing hard on getting back to the moon. And one of the reasons for that is that there is a certain group of humans that are explorers that want to take extraordinary risks and be out on the edge of things. And when we don't give them things to do, they do really dumb things. So we might as well help facilitate them, do stuff useful, and be an inspiration, drive forward technology. Like, there's constructive ways to use all of that. All right, maybe some justification here. So let's talk a little bit about how we go about it. And the most important part then is getting into orbit. The author Robert Heinlein many years ago said once you get to Earth orbit, you're about halfway to anywhere in the solar system. It's actually the hard part. It takes a lot of energy to get moving fast enough to still be around the Earth but not run into it. When we actually do a launch into space, most of the energy is to accelerate us, to increase our speed by about 25,000 kilometers per hour so that we keep falling towards the Earth and missing. There's the idea of a space elevator as a simpler solution to this. If we're really going to drive down the course of going into orbit, let's just lay a cable from geostationary orbit, which is about 36,800 kilometers up, down to the surface. It wouldn't be held up. It would be balanced. You'd have a counterweight further out. The problem is that the materials strong enough to take the stress of doing that are unobtainium. We've made small quantities of like diamond nanotubes and things that rate for sufficient strength, but you need millions of kilometers of this stuff woven together into strips. And even if you could get the materials figured out and build this thing, you'd probably want to capture an asteroid and put it into an extended orbit and then build off of that down to the surface. When you get all of that done, and you're good enough to actually build a material that can handle the weather and the stress, something strong enough that even if an airplane impacted, it wouldn't affect it, you still have the problem that it's a 36,000 kilometer long ride on the equator up to geostationary orbit. So you're going to have an elevator you're going to be in for a while. And while you're in that elevator, you're going to pass through the Van Allen belts, which are two highly charged bands around the planet caused by our magnetosphere interacting with the solar wind. Now we have, normally when you're dealing with a space shuttle or the space station, they're underneath the Van Allen belts. They don't go that far out. But when we sent astronauts to the moon, we did send them through the Van Allen belts, but we did it at velocity. They went through it in minutes. They also went through it through the poles, so they minimized their exposure to the Van Allen belts. If you put a space elevator, which you have to put on the equator, just for balance sake, you're going to go through the thickest bands of these high radiation zones. That's fine for cargo, but it's not fine for humans. And we really have not developed good radiation protection systems. So there's really hard problems to solve on space elevators. And it may not be necessary. Because the current generation of spacecraft that we're playing with now are largely becoming reusable. The Falcon 9, and listen, I'm really frustrated with Elon. I mean, the guy who flew his sports car into space, that was a fun guy. I don't know who this guy is. But the reality is the Falcon 9 now has landed its first stage over 400 times. One of them, I think, is up to 27 or 28 times. Like, he's cut the price of lifting mass into space tenfold. Before SpaceX, it was about $20,000 a kilo to low Earth orbit, and now it's less than $2,000. And you can actually rent a spacecraft to go into orbit if you wish. It's about $100 million, so save up. But you and 3 of your friends, and they got to be pretty good friends, can spend a week in orbit. And a few times this has happened, typically the toys of billionaires. You will also quickly discover that you will be space sick the whole time. Astronauts are not normal humans. But this is actually a picture of Starship, which is the experimental vehicle they're still developing. It is extremely large. It's the largest spacecraft built so far. And it's supposed to be 100% reusable. So the booster will go up, flies about 2.5 minutes, and then separates from the upper stage, would then turn around, go back, and be caught out of the air by the control arms on the landing pad, which seems absurd, except they've done it. So, okay. And then the upper stage would actually go into orbit with a payload of up to 100 tons, which is a lot, and then be able to deorbit, re-enter, and land back at the pad, and also be caught by the arms to be landed, which has never happened. In fact, they haven't actually left a Starship in orbit for any length of time yet. It's always been suborbital. And the last 2 flights they had didn't go particularly well. They were rather explodey. Now, here's the miracle. That is a 30-story building that weighs 200 tons being caught out of the air. I did not expect this to work. And it worked more than once. So that's already profound and insane. But they still have to figure out the upper stage. So I think that's flight 8, which,
water landing. Just the water
yes, a well-distributed water landing. And I think, there was actually. So there was something wrong with the version 2 of Starship. It looks like there's a harmonic resonance in it, and so the 2 times that they've flown it, both times just as it's reaching orbit, something breaks and the fuel system leaks and the lower part explodes and you have a hardware distribution problem. But in theory, should this vehicle finally function as designed, we should be able to lower the price tenfold again. This should be $200 a kilo. Some argue less than that. And now you're talking about trip of a lifetime for regular people. You know, like the equivalent of going to the Galapagos, maybe $20,000 a person instead of $20 million a person. And just being able to deploy a lot more stuff into space. The vessel itself is 9 meters in diameter, which is extraordinarily large. You could take 2 James Webb Space Telescopes unfolded and put it in that space and fly them. So it's really a large vehicle, and it opens tremendous possibilities. They're not the only ones. Blue Origin, this is Jeff Bezos's company, has finally flown their New Glenn rocket. This is a 7-meter rocket, so it's not quite as large. It's supposed to be recoverable, but they've never recovered one yet, but they have at least flown one. So there is some sense that there's competition coming here. SpaceX has a massive lead, irrespective of Elon's current generation of insanity. So, yeah, that's New Glenn flying for the first time. And again, 7 meters is very, very big. The first stage of the Saturn V that went to the moon was a 10-meter first stage, but then it got progressively smaller. This is 7 meters all the way up, and so we've never had so much volume going up into space. We've done with these latest ones. So here's the current estimates of pricing. These are the only numbers in this whole deck. And then get back to that point of just how much cheaper Falcon 9 is compared to anything else. The Vulcan numbers are sort of artificial. A reminder that Space Launch System, which is the repurposing of the space shuttle, is catastrophically expensive. So one of the things that NASA is really good at, because they're funded through their Congress, is that over time they managed to get the space shuttle built, have some part of it built or maintained in every single state in the United States. And so even when they had to stop using shuttle because it was wildly dangerous and they had lost 2 and couldn't replace them, the Congress insisted that they continue to keep all those people employed. And so the proposal then was to build a new vehicle from the same technology. And that's the Space Launch System. It's literally using the rocket engine, the engines from the shuttle with the same kind of boosters, but they only funded it enough. NASA didn't want it. So they would keep trying to write it out of the budget, and the Congress would always put it back, but they'd only put it back enough to just keep everybody employed. The problem is that eventually they managed to actually build this rocket. And so now they have this incredibly expensive rocket to operate. We do have the space station, which was built largely by the space shuttle. It is aging out. We'll lose it in probably, it was originally supposed to only be used to 2024. You'll notice we're still using it. Now supposedly end in 2030. They've now given the contract to SpaceX to deorbit it. It seems like a waste, but it isn't actually. There's a bunch of problems. The main one here is actually it's too big. So they've spent a lot of time trying to find stuff on it. The core modules, the modules that the Russians originally flew that are now 25 years old, are the aluminum is becoming embrittled. So it's starting to crack and it's starting to leak. There is mold growth and things in the walls, essentially. One of the ideas would be to replace the core modules, leave the other modules in place. The problem is that the berthing approach, where they just put the 2 pieces together, they were designed to be assembled. They're not designed to be disassembled. There's a weird effect that happens in orbit where those 2 pieces of metal actually weld together. They're 1 piece of metal now. And there's no expectation they could take any component off and remove it from the space station. They're all fused. So you would have to, if you were going to try and salvage some of the newer parts, the parts towards the frontier, you would literally have to build a different core module onto it. And the difficulty there, it's easier to just fly a new station. In fact, the proposal now is to stop making a giant station, but to make a bunch of smaller stations for different missions, different purposes. So NASA wants to get out of the space station business entirely, at least in low Earth orbit. So they have this thing called the Commercial Low Earth Orbit Destinations Program, where they want to buy time on space stations. So industry will build stations to certain specifications and they'll utilize them. And one of the reasons to build a series of smaller stations is so you can do different kinds of experiments. For better or worse, the International Space Station has only ever been used as a microgravity laboratory, primarily for humans. We've learned a lot about humans' behavior in microgravity, which mostly is a way to say it's not good. Humans are not good in microgravity. You have to exercise 2.5 hours a day to limit the amount of bone loss. You have cerebral spinal fluid, which normally gets pumped down into your spine through gravity, and it doesn't happen in free fall. So their faces all puff up, and they end up having to wear different types of glasses, and it changes the shape of their eyes. It's damaging. After 6 months in orbit, which is the normal duration on a space station, you need about a year's recovery time. It's just hard to get healthy again. And these are also astronauts, which are not normal humans, right? They're the guys who are willing to work hard enough to get 3 degrees. There was a group of spacewalkers while they were building this station that were having problems with their gloves. And because the gloves are pressurized and they had to do all this physical work while they were assembling the station, that their fingernails would bend back and it would make their fingers bloody. So they had their fingernails surgically removed. Astronauts are not normal humans. Regular people are not going to do this sort of thing. So it's hard up there. Anyway, there's a bunch of station proposals. This is one of the Blue Origin ones. It's called Orbital Reef. It's based on the New Glenn rocket. And this is actually a triple station. It's much bigger than they would likely actually build. And there are a bunch of others. Axiom Space has actually built a couple of modules now, although they're running out of money. Their goal was to actually get their station built while the space station was still up so that they could use the berthing mechanism. Instead of having to put engines and guidance on every module so that they can dock themselves, have it just get to the station so the arm can grab it and berth it and assemble another station beside the existing station on the PMA, which is the adapter that is removable, and then hopefully have it done in time that before they deorbit, they can separate off and make a standalone station. Right? That was their goal, was to try and do that. And originally there was a proposal to take some of the existing components off the space station with them, except when they actually did the test to say, is this possible? It's like, no, all these components have been up here a few years and they're fused together and they'll never separate. And then there's a crypto billionaire, a guy named Jed McCaleb, is now building, he's already bent metal on Haven 1, which he can fly off of a Falcon 9. So they are making their first station. They want to launch their prototype this year. So they're trying to get ahead of the whole thing. And it's just, it doesn't make crypto billionaires any nicer people, but there's a lot of people trying to do stuff. So I'm giving you a sense here that we've done a lot in low Earth orbit already. We have a bunch of different components moving at once. There is life after the International Space Station. Let's not neglect the fact that the Chinese have been now continuously occupying their space station, the Tiangchen, now for 4 years. There's 3 taikonauts up there right now. So we're going to have more stations, and we can do different experiments with them. It's just a question of time. Okay, let's talk a bit about the moon, because the moon plays an important factor in where we're going here. This is my favorite picture of the moon for a couple of reasons. The first is a picture of the far side of the moon. Clearly, it is not the dark side of the moon. That is a record album, one I quite like. The real question you have to ask when you see a picture like this is, who took this picture? This is a tricky picture to take. This is a photograph taken by the Discover satellite, which is actually a solar monitoring spacecraft in the Lagrange point 1 of the Earth-Sun system. So this is a gravitationally stable location between the Sun and the Earth, about 1.5 million kilometers away from the Earth. And its principal job is to monitor the Sun, looking for coronal mass ejections and other events that come from the Sun that could impact the Earth. And somebody was clever enough to put a telescope on the backside of the satellite. And it is a telescope because this is 1.5 million kilometers away. And that telescope always has a perfect picture of the disk of the Earth because it's in the Lagrange point, so it's always facing the Sun and the Earth at the same time. It's always going to have a full disk lit of the Earth. And so it takes photos on a regular basis, which are published publicly. You can get them anytime you want. And every so often in that picture set, the moon whizzes through the frame. There'll be like 3 pictures of the moon. And it's moving so fast that you can also see a flaw in this picture if you get up close to it, which is that the camera's not actually a color camera. It's a black and white CCD with different filters. And so to make a color picture, they actually take 4 photographs. And in that time of taking those 4 pictures, the moon moves. And so if you get up close to this, you'll see that along the right edge of the moon is a green haze, because the green is taken last. And the moon's actually moved a bit, a little out of proportion, which would be a heck of a CGI trick to pull off. But it's a real photograph. Well, the humans have already been to the moon. That was the Apollo missions back in the 60s. If you aren't clear that it was actually a military mission to prove American superiority over Soviet technology, here are the 12 men that walked on the moon. 11 of them are test pilots. One of them, this guy, Jack Schmitt, is the geologist. So the rest are all test pilots. And they did test piloty things, right? They spent time on the moon. Jack was supposed to be on Apollo 18, and he also trained all the astronauts in geology, because he was a geologist. And when they canceled 18, they sort of freaked out. It's like, we got to send at least one scientist to the moon, so they bumped him up to Apollo 17. He went there with Gene Cernan. There's Jack on the moon. You'll notice he's a little dirty, because Jack's a geologist, and geologists really like rocks. And so Jack is looking at the rocks. And Jack cared about looking at the rocks more than he cared even that he was on the moon. In fact, he endangered his life routinely on the moon, because they wear this gold shield over their face because the sunlight is completely unfiltered and it'll burn your retinas out in an instant, and the gold shield protects you from that. But the gold shield changes the color of the rocks. Jack really likes rocks, so he kept lifting his shield up. In fact, he's the only person to ever have a picture of his face on the moon, because he kept lifting his shield up, because he's a geologist. The other guys are test pilots. What are test pilots thinking while they're on the moon? Don't screw up, don't screw up, don't screw up, don't screw up. Jack's thinking, that's a cool rock. And the shield got in the way. And so all of the telemetry from the 3 days they're on the moon is on YouTube if you want to listen to it. And you'll hear Capcom saying it over and over. And Jack, when you get a sec, would you put your shield down, please? You dumbass. So Jack started doing things like, if you look close on this picture, see the side of his helmet right there? There's little bits of paper. So on your left arm in the Apollo suit is literally the minute-by-minute timeline of what you're supposed to be doing while you're on the moon. And as Jack was finishing each page, he was ripping them off and sticking them in the helmet to make a sun shield so he could lift his visor to look at the rocks. That's how much Jack wanted to look at rocks. And he found the best rocks, because he's an expert. And let's face it, like, real science isn't done by, eureka, I found it. Real science is done by, what the hell is that? And he was able to find a piece of unshocked olivine on the moon. And if you were a geologist, you'd go, ooh. And to the rest of us, like, what? Well, an unshocked piece of olivine is proof of a volcanic eruption on the moon. It's the only way you would end up with that kind of rock. It has to be done in a volcanic compression. And he proved that there used to be volcanic activity on the moon by finding the physical evidence of it. And it begs the question, what would happen if we could leave scientists up there? What would they find? Right? There are different species of human again. The Apollo missions had to end, mostly because of this machine. The Lunar Explorer module, the LEM, was a very dangerous machine. It just barely was able to do its job. There was a whole series of failure modes here that if any of them occurred, there was no way to save the astronauts. They only had 3 days worth of supplies on that thing, and it took more than 3 days to launch a rescue mission. So there's just nothing they could do. And the administration very nearly canceled after Apollo 8. Once they made it around the moon with humans, they'd beaten the Soviets at that point. So it's like, let's stop before anything bad happens. It's like, no, Kennedy said we'll land on the moon. So, okay, then they get to Apollo 11. Okay, we've landed on the moon. Now stop. No, we got all these other missions. So they got as far as 17, right? They had the 13 incident where an explosion happened and they nearly lost those guys too. So in the end, they made their point, they did their thing, and they haven't been back. It's very dangerous stuff. But technology evolves, and they have this new vehicle, and they have a new set of missions they're calling Artemis. Artemis was the sister to Apollo. There's where the name comes from. So they've flown Artemis 1, which was an unmanned mission using the new Orion command module, which is much larger than the Apollo modules. It'll hold more people, more resources. It's a vastly superior vehicle. And they tested it around the moon. They did a lot of orbital tricks. We know have a lot more computing power and a lot more software around orbital maneuvering. And so there was an opportunity to experiment with that with this vehicle and showed some really powerful capabilities. We are much better in space than we've ever been before. So that mission ran back in 22 and came back safely. The next one was supposed to fly 2 years later in 2024, and that's Artemis 2, which is basically a recreation of Apollo 8. They were going to take 4 astronauts, and 1 Canadian, 3 Americans, and fly them around the moon and back. Free return trajectory, basically a complete replay of Apollo 8. That's now been bumped out to 2026. The astronauts have been selected, the vehicle's under construction and testing, so that should happen sometime, maybe this year, maybe next year. That would then be followed by Artemis 3, which should actually be landing on the moon. Now, in order to land on the moon, you need a lander. And in the Apollo missions, they brought the lander with them. It was this is what they called a direct ascent approach, where you brought both your command vehicle and the lander all in one flight. They don't want to do that this time. What they really wanted was a fully reusable lander. The LEM was a 2-part lander. It had a descent stage and an ascent stage, and the descent stage stayed behind. And if you're actually going to build a base on the moon that people are going to go to repeatedly, you can't be leaving parts of your spacecraft behind every time. It's expensive and messy. It's like a parking space you can only use once. So they asked for proposals for a fully reusable lander. And the only one that actually that proposed something that was even possible was SpaceX with a modified version of Starship. Now, there's some problems with this design, but it is fully reusable in theory, not that they've successfully built it yet, but it's 60 meters high and mostly fuel tank. So there's the people down there. This is all fuel tank. This is where the people and the cargo goes, so watch that first step. So they're going to be an elevator, and you better find a flat spot to land because that thing tips over. Everybody's going to have a bad day, but this is the current proposal. There's more problems. In order to actually do this, because it uses most of its fuel to get into orbit, you're actually going to need to refuel a spacecraft. Nobody's really sure how many times, because they're not really sure how much they can carry up of excess fuel to transfer to the other one, and nobody's ever refueled anything in orbit, ever. In fact, it's one of the core skills we're going to have to develop if we're going to be a spacefaring civilization, is to refuel a spacecraft in orbit. And there's been a few drawings that are all like HR violations. Like, I'm a little uncomfortable with this picture. Anyway, and there's problems. Free fall makes things tricky, right? Here's an example. This is a video of inside of a Falcon 9 liquid oxygen tank under acceleration. Can you see when the acceleration stopped? So now that we're in free fall, the liquid sloshes around inside the tank. And that means you can't pump it. So when a second stage has gotten to orbit and shuts down its engines, typically they'll have to wait to a particular point to do another burn to raise the orbit. If the fuel's moving around like this, the engines aren't going to start. In fact, they're likely to explode. And so what they have to do is they fire what are called vernier thrusters, little gas thrusters. They just accelerate the vehicle a little bit to settle the fuel down so then they can relight the main engine and take off again. If you ever watch a SpaceX launch, you'll see these moments where the engine shut off, then wait 20 minutes or so forth, and you'll see these little thrusters fire up for a little while, and then the engine lights and off it goes again. Now, if you're going to do that for refueling, you're going to change orbits when you do that. This is also somehow inappropriate, but okay, now we're going end to end where all the plumbing is, but now you've got to get the fuel to settle in one way or the other. I'm not sure which way. There's a lot of problems to creating refueling and not moving the vehicles around too much. One of the best ideas I've seen is this, where we actually dock the tankers to a central structure, and when we need to pump fuel, we spin the whole structure. So we fire up a little thruster, so now we're not changing orbits, we're just rotating, and that's enough to move all the fuel down level of the tanks. Now you can pump the fuel where you need to go. This is a depot. This is infrastructure. It's a gas station in orbit. You know, arguably, if you go down this path now, rather than having to wait for multiple refuelings before you fly to the moon, you get all your fuel up there already, then the vehicle comes up, fuels once, and then heads off to the moon. And if you're really smart, you make a market where you say, hey, I'll pay this much per kilo for liquid oxygen and liquid methane. I don't care where you get it from. If you think you can fly it cheap enough from the Earth, knock yourself out. You want to extract it from the moon and bring it back? Fine. We could build a depot like this in orbit around the moon as well, so you can have a fuel store there and just supply it with whatever means you can. So we start to think in terms of infrastructure in space. The first decade or so that the automobile existed, there were no gas stations. You bought your gas from the chemist in bags because it was a hobby thing, right? The gas station only starts to exist when roads start to mature and there's more cars around. We've been flying into space carrying everything we need with us every time so far. We've never had infrastructure in space, stuff that can be reusable, stuff that would reduce weight and you only use it when you need it, that kind of thing. So this is the beginning of that idea, that we start to put depots and buy product where we can get it and be able to provide additional energy where people are needing to pay for it. So we have the problems with this particular lander. There are other landers proposed, but none of them are fully reusable. This is the Blue Origin version, which is actually a 3-part. So this is the descent stage is all this lower part with the cargo on it. That little module at the top is the only part that would go back into space. That's the ascent stage. So they didn't do what NASA asked, make a reusable one. They made a multi-part, much like the previous one. Actually, the most important thing in this picture is the fact that that astronaut is kneeling, because the Apollo astronauts couldn't kneel. The suits are little spacecraft that you're wearing, and they're pressurized with air. And it limits your ability to move. If you watch the astronauts moving around the moon, they kind of do one of these Michelin Man things, because they're basically not fighting the ankles of the suit to minimize the amount of energy they put into it. But ATK believes they can have a suit now that where they can reduce the pressure enough that you could fully articulate your knees and be able to move around more. Also, NASA wants suits that last. The longest any suit functioned on the moon was about 22 hours. They want an 800-hour suit. And the moon is covered in very abrasive dust that gets into absolutely everything and damages everything. So making an 800-hour suit seems extremely difficult. There's a couple of cool ideas on doing this. One of them is using electrostatics to drive the dust off. So the dust is ionic, and so you can basically they've demonstrated actually with a lander on the moon just recently, they put down a little piece of this material, and when the lander landed, dust landed on that, and then they have a camera over it, and they fired up the power through the mess, and all the dust went, boop, jumped off. So you can imagine wearing that in your suit, and you can de-dust yourself, essentially, by charging it. Now, the Apollo astronauts only landed roughly in areas around the equator on the near side of the moon. That was mostly a limitation of the technologies in the 60s. If we really want to do research on the moon, science on the moon, we have to go where the science opportunities are. And where the Apollo astronauts went was very much like you've only landed in the Sahara Desert and that's all you know about the Earth. They landed in sort of the driest, kind of least interesting areas of the moon, but that's where they could go. The interesting areas of the moon are on the poles, and so the proposal is to land on the South Pole, specifically around Shackleton Crater. And the reason for that is ice. There's a lot of water ice in it. Here's Shackleton Crater over a year, and you can see the edges of the crater almost continuously lit, but the inside of the crater never gets light. And you should ask the question, who took this picture? So this picture is a composite of photographs from the Lunar Reconnaissance Orbiter, which has been in orbit around the moon since 2009, and it has done the detailed photographs of the moon. It's the first thing that ever took pictures of the Apollo sites where you could see the footprints and the pieces left over and so forth. I mean, since then, the Russians have taken photos of the Apollo sites, the Indians have taken pictures of the sites, China has taken photos of the sites. This is a demonstration of how much better their cameras are, that they can take pictures, higher resolution pictures than LRO, but admittedly, LRO is now 17 years old, so give it a break. But every time it made a pass over Shackleton, they would add a photo, and then they lined them all up over the 10 series of the year, and so you can see that the rims are always lit, the inside's always dark, and there's several billion tons of ice in there. This crater is bigger than you think. It's 21 kilometers across. So you could fit a few cities in here. And there's a lot of ice in there. So the idea is build the base on the rim and then do exploration into the crater. And the goal is to extract water ice and then turn it into fuel and air. That would be the first time we've ever used resources off the moon, so we don't have to carry them. So you can imagine building up the infrastructure to supply oxygen to the base so you don't have to keep bringing more. The space station gets resupplied every quarter with air and water and supplies. because it's close enough. It's about 8 hours it takes from launch to actually docking with the space station to provide it with supplies. The moon's 3 days away, plus you've got to land, which is not a trivial effort. We can't keep bringing all the supplies up. It's not economically viable. So being able to start extracting resources from the moon, especially heavy stuff. I don't know if you know this, but water, a liter of water weighs a kilogram. That adds up. It's just expensive. So if we could start getting water from the moon and not have to lift that much, just enough we need for the trip, we could save a lot. There is a proposal to put a form of GPS around the moon because we need precision navigation. This is actually proposed by the European Space Station. It's called Moonlight. And it's a combination. It needs far few satellites. The moon is quite a bit smaller. It's roughly the same surface area as Australia, more or less, total. The orbits are a bit unusual, but you'd be able to do precision location and communications. There is one satellite like this already on the, up around the moon. It's the Chinese put it up. It's on the far side of the moon. It's in the L1 Earth-Moon setup, and it's for telemetry for China's landers on the far side of the moon. They're the only ones to have landed anything on the far side of the moon, and so they have this satellite to do telemetry for them to communicate back to the Earth, otherwise they can't communicate. So the proposal here is to put up, I think it's 16 satellites total that would provide a web. So you'd have precision navigation and precision communications, which means you carry less stuff on your spacecraft. Right? Instead of having a triply redundant navigation system and radio system, you have singly redundant because you also have the existing orbital system as well. So you carry less weight, you have more flexibility, you can do more stuff. Elon proposed a base on the moon that looks disturbingly like Burning Man. I also thought it looked like Space 1999. Anybody remember that show? It's a while ago. Don't watch it. Your childhood memories of this show are vastly superior to the show. You will ruin your childhood if you watch this show again. Ask me how I know. But yeah, it doesn't make sense to build a base like this. The radiation exposure is really serious. Micrometeoroid exposure is serious. When the European Space Agency was originally proposing this, what led to this talk and all of this stuff, they were talking about building small inflatable habitats that they would use remote control robots to bury under a meter of regolith to provide radiation protection. So it wouldn't be very big, but it would be protected and you would be safe from radiation there. There's another alternative, and that is to use skylights. So we know there was volcanic activity on the moon. There was eruptions, and there were large lava flows. That's what the mares are, or the mares, depending on your language. And so wherever there's volcanic flows, there are volcanic tubes. So as the lava pushes through the regolith and then hardens up, it creates a tunnel, and then when that lava drains away again, it leaves the tunnel behind. And in spots, it's close enough to the surface that over time, the roof of it collapses. This is the Marius skylight. So this is a point where one of those lava tubes has broken open, and that opening is very large. They figure about 65 meters across and about 80 meters deep, and nobody knows exactly how far it would go. There's a Japanese mission now to actually put something down there and start taking some look as to how far it would go, but there's an idea then that we fly an inflatable habitat, land it in there, slide it into the tunnel, and inflate it. And now you have built-in protection, a lot of space, and you get that cool Dr. No rockets taking off out of the inside of the moon thing, which is a feature. But not necessarily where you want to be, because then we got to go to the next steps on what do we do on the moon. It's not just about extracting water ice. Water ice is huge, but we should be able to prospect, mine, extract resources, and smelt them. And there are a lot of good ores on the moon, stuff that you need. Aluminum, titanium, various kinds of irons. We could build refining machines up there and start pulling all these. Actually, if you look at the list of elements, it's everything you need to build solar panels. Solar panels, when you make them, are actually crystals. And one of the things that affects the structure of a crystal is gravity. So there's this pretty good argument that if we got to the point of actually doing mining extraction, we could start growing the silicon dioxide crystals for solar cells that would probably be superior to the ones we can make on the Earth, just from the reduction in gravity that you get on the moon. Now the Japanese said, hey, why don't we just build a band of solar panels all the way around the moon? I mean, it's just like building a strip of solar panels from East Coast to West Coast Australia. I mean, how hard could it be? Probably excessive, but certainly making our own solar panels up there is useful for the power that you'd need up there. But another interesting proposal is to make solar panels for use by the Earth, not back on the surface, but in orbit. So you build up your manufacturing capability, and then you can, because the gravity level is so low on the moon, it's very easy to get back off the moon and head back towards the Earth. It's hard to get off the Earth. It's easy to get off the moon. So you could propel them back off of the moon to geostationary orbit to build space-based power arrays. This is a design called SBS Alpha. It just looks disturbingly like a margarita glass, but let's not hold that against it. It's big. It's about 5 kilometers across, and that's the real problem. We can build this today. There's no technology missing here that we need to invent, but it's so much mass to lift from the Earth, it's cost prohibitive. But if we had matured those technologies on the moon to manufacture the key parts of this and then use linear accelerators to fling it back to the Earth from the moon, you should be able to reduce the cost enough. And this, at that scale, that's a gigawatt power plant. It's an entire nuclear power plant, and it's solar powered. And because it's in geostationary orbit, it has 24-hour-a-day sunlight. So you always have energy there. Now, what do you do with that energy? Well, down at the bottom is a rectenna, which converts that solar energy into microwaves, and then you can transmit them on the surface of the Earth. This is an existing technology. We use it today. This would be a larger version of that. And a typical 1 kilometer array beaming a gigawatt of power would land in a 10-kilometer circle. Now, the energy density would be low enough. You're not going to cook birds in flight. But you really shouldn't be walking around in there either, so you probably want to put a fence up. But it's a gigawatt of zero carbon energy, and it's steerable. So you build a few of these things, you can lay down power in a natural disaster site where systems are broken and you need to put a little power down, you could do that. And it's a way to decarbonize energy production in a way that's really quite effective. You could also point it elsewhere. It doesn't have to go to the moon. It's more infrastructure. You know, every spacecraft has a combination of a power source, a propellant, and an engine. Now, often we're using chemical propellants, which are a combination of the energy and the propellant itself, but we also have electric propulsion, Hall effect thrusters, where we use big solar arrays to generate electricity to superheat xenon to propel out the back of a Hall effect thruster. It's an electric engine. Well, what if you could offload the power? What if you could build one of those big arrays and then aim it at the spacecraft? So you take the power plant off the spacecraft, make it a little lighter. Especially between the Earth and the moon, where you're going to be sending stuff back and forth all the time as you're making things and sending up supplies. To have one of these power plants essentially provide the energy to accelerate and decelerate the vehicle, now the vehicle gets simpler, and you're starting to build a bus lane in orbit. It makes it easy to travel between those 2 points. So if you've built up the skills to extract resources from the moon and utilize them in different places, you're ready to go to the next step. And the next step is to start extracting resources from asteroids. So now we're locating different resource points. Now, generally speaking, an asteroid is going to be heavy enough that you don't really want to move it from where it is, so you're essentially going to build the refinery to go to it. Now, we've done a bunch of exploration on all of this. I've already done geek outs on this particular subject if you want to go back and listen to them. There's a lot of matter out there in a lot of different forms. There are different classes of asteroid. Some of them are full of water and volatiles. Some of them are full of silicates. Some of them are full of heavier metals. There's every kind you can think of. The C types are the most common. These are the carboniferous. So nitrogen, water, potassium, phosphorus. Then you have the S types, which is what Didymos and Dimorphos are. And so that's silicates. And then you have the true metallics, what we call the M type. The largest of them is Psyche, which we currently have a mission going to. And this is nickels and irons and platinum class metals. So you take what we've already learned. Now you're working in very low gravity. We've already started building experimental bits of vehicles designed to do this, to capture smaller asteroids in a containment and then use solar energy to vaporize the rock and chemically extract the resources from it and separate them. These guys, this is called a honeybee, and this this company has actually built their prototypes for optical mining, for doing material vaporization. So you basically vaporize the entire asteroid, sort it into its component parts, put those into bags, and then fly the concentrated assets back. So you don't bring the whole thing back and forth. You just send back what you want. So the logical place to do this from would be the far side of the moon. So on the far side of the moon, you're already outside of a lot of gravity well. So we build out a base up there. We're already doing our mining extraction on the moon as well. But now we can start sending out these extractors to various asteroids. There's a whole set of asteroids that orbit within the Earth system. So we have both what we call Trojan and Apollo asteroids that run roughly about a third of the way behind the Earth and a third of the way in front of the Earth. It's a gravitationally stable spot. So it's not that hard to get there. You just have to slow down a little, and you'll catch up with a bunch of those asteroids. You get the resources from them, and then when you want to ship it back to the moon, same thing. You slow it down a little, it'll actually drift back to the moon, you pick them up, you build with them. Now you can, in theory, deorbit back to the Earth, but that's probably not as practical as it is just to utilize it in space. So stop building stuff on the Earth that then you have to fold up inside a fairing and launch into space. Build it at scale in orbit with the resources you have in orbit. So now we're going to be working on construction techniques to build a scale in low gravity. A lot of robotics and using the local materials that we're able to extract from the asteroids. But none of this is impossible. This is just incremental improvements in the technologies we already use. It's things we can learn from the work we're already doing on the moon. From the far side of the moon, it's also a place we could actually put a space elevator, because there's no atmosphere to battle. There's much lower gravity. And the materials are relatively straightforward, so the logical place to put it is actually on the far side of the moon. So that you think about where it's rotating. As the moon orbits around the Earth, it's already pointed a fair ways out of space, so it's almost a free launch to anywhere you want in the space, in the solar system. From an orbiting station like this on the moon, you need very little energy to head off to Mars, or to head inward to Venus, or to the main asteroid belt and the outer solar system. So more infrastructure. We have refueling depots. We have energy generation points. And we have these launch points for exploring more of the solar system. And one would argue, are we making sense then to maybe go to something like Venus? Like we've built stations around the Earth. We could build a station around the moon. There's a proposal to do that. We're also learning how humans cope in space. And so one of the problems if we're going to explore the rest of the solar system is simply that humans don't do well in space, right? After 6 months, you need a year's worth of recovery. Like they're talking about flying astronauts to the Mars, which takes about 6 months. When you spend 6 months on the space station and then go back to the Earth, there's people to help you. You fly some folks out to Mars, nobody to help them there. What are they supposed to do? So realistically, we can't fly humans for 6 months to get to anywhere in the solar system if we don't have artificial gravity. Now, this is not Star Trek. We don't have magic artificial gravity. The only way we know how to make gravity is to create rotating structures. We've just never done it because it's expensive. And it has to be big enough to be comfortable. There's a graph that basically describes the comfort zone. You can build a smaller structure rotating fast and get 1 g of gravity, but you're going to be messing with your balance all the time. If you actually need to rotate fast enough to create 1 g, which is that upper part of that band, you're really talking about a structure nearly 100 meters in diameter. That's really big. Now, it doesn't have to be solid the whole way. You could have 2 containers with a cable in between. But we haven't done any of these experiments. We also don't know if you need 1 g to stay healthy. We know that free fall is not enough, that microgravity is not enough. But maybe a third of a g is enough, the gravity of Mars. Or maybe a sixth of a g is enough, the gravity of the moon. I mean, one of the experiments if we start having bases on the moon would be, how well does the human body cope if it has a sixth of a g all of the time? Because building a spacecraft that created sixth of a g is a lot easier than 1 g. This is all data we don't have yet. We've never had extended stays in reduced gravity, but we could. NASA's proposed various vehicles that could have a rotating structure. This is called a Nautilus X, and that inflated ring would be the rotating part. And the challenge here is that most of the vehicle isn't rotating. So now the astronaut would have this interesting problem where they probably sleep in the rotating structure so that they stay healthy, but they work in free fall. And we know even for astronauts, it takes 2 or 3 days to adapt to microgravity, and then you stay in microgravity. And then when you have to de-adapt, it takes time to recover as well. So what if they were switching every day? We don't know what that looks like yet. It might be really hard, or maybe they get used to it. I don't know the answer to that. In the movie The Martian, the vehicle they called Hermes is actually a really well-designed, large-scale explorer vehicle. I mean, I know it's fiction, but it was well-written fiction. And they had this rotating structure in the middle of the vehicle with only 4 compartments on it. The rest is just truss rotating. And that looks like it's about 100 meters, rotating at about 4 revolutions per minute, which is about a G. And then mostly a nuclear-powered vehicle. And this would be such a large vehicle, you'd have to assemble it in space. So it wouldn't make sense to build from Earth, per se. And arguably, that vehicle would be in what's called a cyclar orbit. So it would fly between the Earth and the Moon gravitationally. It's about 6 months to go to the Moon and about 30 months to come back, over and over and over again. Once you get up to speed, it stays there. And you've got all that extra mass of the rotating structure and so forth, so you just leave it in that cycling orbit. Probably have a few of them. And then you use fast vehicles with the passengers on them and the supplies to catch up with the cycler, dock, drop your supplies off. Now you have your gravity and your radiation protection and so forth, and you make your flight between the planets. But I would also argue that going to planets is kind of dumb. Like, it sounds like the terraforming of Mars thing is coming up again. Not that we've been terraforming the Earth, not for the better, but we've been doing it. I would think that Mars is a good place to go to explore what's there. It's distinctly possible that there's life in the waters under the soils of Mars, the remains of the life that was there when it was a warmer and wetter place before their atmosphere got stripped away by the sun, when their magnetic field collapsed. If you really want to put humans off planet, living at scale, rather than trying to populate another gravity well, build them. You've learned all the things at this point. You're extracting resources, you're building spacecraft. So build a habitat, build a really big habitat. So this is an O'Neill cylinder. So 5 kilometers long, 1 kilometer in diameter, reflectors on the outside, they collect energy as well as provide sunlight, rotating very slowly to create 1G. So you live inside of the curve. And one of these could hold somewhere between 200,000 and 1 million people, depending on population density. And we have enough material in the solar system to build tens of millions of these if we care to. And you just leave them in orbit. I wouldn't put them in Earth orbit. I'd probably tuck them a little further in. There's more energy if you get a little closer into the orbit of Venus. And you still will have your normal gravity. And if you want to go into space, you take an elevator. You go to the center axis where there's no gravity and you fly out from there. So you have all the benefits and you get your own habitat. We could build a lot of these. You want to get 1 trillion humans. I don't know if you do, but if you wanted 1 trillion humans, you'd build several thousand of these. And you leave the planets alone. You don't really need them. We've got enough materials elsewhere to build these things, and you can create the worlds you want to create. This feels like science fiction, but I hope over an hour I've given you a path. We're on the path to being able to build these things. With each step, better in orbit, building out resources to extract from the moon efficiently, learning to gather the materials on the moon and utilize them, then turn to asteroids, do more construction in space, build larger vehicles, and ultimately build these big habitats. That's how you become a spacefaring civilization. And that's all I got for you. I hope this was fun. Thank you.